Hello, class. If you're watching this video, you're probably taking my online class or my hybrid class. But the page you're looking at right now is the same page that I'd be projecting in my traditional face-to-face in-person class. Generally, I'd project pages from the textbook in my lecture hall or in my classroom, and I'd go through the book with you with examples and problems, and that's what I plan to do in the next set of videos. Okay, so I'm trying to really replicate what you would get if you were coming to me live in person inside the classroom. So this course deals with a lot of problem solving. So the first day I'd like to really tackle the framework that's required to solve problems. Additionally, in this first lesson, I'd like to practice using input-output tables. I'd like to review important definitions and key concepts. And there's also a 1-1 summary I'd like to complete. In fact, I've actually written down my goals for this first video. It is possible that I might have to do maybe 3 or 4 short videos to accomplish all of our goals. So let's begin. Problem solving and numerical representation. This is page 11 in your textbook. Okay, and remember, the ebook is available on Canvas for free. Okay, so it says a framework for problem solving. The following 4 phrases can be identified in the process of solving problems. And I think this kind of makes sense. 1, understand the problem, right? What problem are you trying to solve? 2, make a plan, right? How are you going to attack this problem? You should stop, think about what kind of plan you want to put together to solve the problem. 3, this is where you're going to execute the plan or you're going to carry out the plan. And then 4, many of the problems we encounter, we can kind of look back and almost check our work, right? Did it work as planned, right? Does the solution, is it valid? Okay, so before we discuss, apply this process, there are a couple of definitions and key concepts. So the first one is a variable, right? A variable is usually represented by a letter or a symbol. And many of you have used variables already, right? If I were to say 2x plus 5 equals 10, you might solve for the variable. You might solve for x, right? It's a quantity that may change with the context of a mathematical problem, a placeholder for a specific value. So let me give you a quick example. I just switched to my whiteboard because I can use a tablet on it. All right, so if I were to write something like, I have a new job at Starbucks and my pay, call that letter P, is going to be equal to, let's pretend I make $15 an hour at Starbucks. So for every hour that I work, I get $15. So this could be an equation where the letter P is a variable that stands for my pay, and the letter H would be the number of hours I work. The more hours I work, the greater my pay. So if I were to work, say, 2 hours, right, we could write my pay would be equal to $15 times 2 hours, which equals $30, right? Or if I were to say I work 5 hours or 3 hours or 1 hour, right? If I work 1 hour, my pay would be equal to 15 times 1 or $15, right? So the A is a variable, right? The P is a variable, and you just saw me use these variables to solve a problem, right? I want to figure out how much would I earn if I work 2 hours. Well, it's 15 times 2 is $30. Let's keep moving. Another definition or key concept is an input-output table. An input-output table is a numerical representation of a rule. This table has at least 2 columns, okay? And then, on the last page, I drew an equation. The rule for an input-output table is a symbolic representation. So if we were to go back to, right, this P equals 15H could be considered the symbolic representation of a rule, right? The rule is I get paid $15 for every hour I work. What you see here is a representation, a symbolic representation of that rule. Okay, Oh yeah, that could also be called the formula. So example 1. Okay, so the math department moves to its current location. This is kind of a true story, actually. And we were trying to figure out ways to set up our cubicles. So it looks like this is one suggestion, right? So think of this as a panel, right? 1, 2, 3 panels. So if I just had one person, I would need 1, 2, 3 panels or 3 partitions. To help visualize what a panel might look like or a partition, I have something like this, right? Imagine if we were trying to house horses, right? We might have a partition or a panel that looked like this. This is the side view, the top view. So when I stand them up, right, I could put a horse inside this set. But imagine this was like office furniture now, right? If I were to remove this panel here, and I'd have 1, 2, 3 for faculty to sit with their computer. So maybe you put a faculty member here, and another one in here, and a third one, and so on. That's what this looks like, or if we were looking down on it, right? 1, 2, 3 panels or 3 partitions. Okay. So it says how many partitions will be needed to arrange cubicles in one long row for 30 faculty. So they said, all right, well, let's understand the problem, right? We need to figure out how many of these partitions we need to house 30 faculty, right? Maybe you come up with a plan. What is my plan for solution? Looks like they're suggesting we create an input-output table. Then it says carry out the plan, okay? So here's an input-output table. So think about this. If I had just one faculty member, you would use 3 partitions. And you can see that in the picture up here, right? 1 faculty member, 1, 2, 3 partitions. But if I had 2 faculty members, I'd have 1, 2, 3, 4, 5 partitions. So notice in my input-output table, we wrote 5 for 2. And finally, if we had 3 faculty members, right, we would use 7 partitions. Let's just double check, right? 3 faculty, 1, 2, 3, 4, 5, 6, 7. And if I wanted 4 faculty, I'd have 7, 8, 9, 10, 11, right? So it looks like we need 3 partitions for the first faculty member and then only 2 more partitions for each additional member, right? When you look, we start at 3 and the number goes up by 2 every time, okay? So if I asked you to make a rule that describes what's happening in this table, you could write y equals 2x plus 1. So if I want to test the y equals 2x plus 1 rule, remember x is over here, the input, and y is the output. So the input was the number of faculty members. So if I put y equals 2 times 1 faculty member plus 1, right? Remember, I'm using this equation down here. I just replaced the x with the input. You get 2 times 1 is 2, plus 1 is 3. And look at that. It worked. Let's try it again. Y equals 2 times, instead of using x, we're replacing the x with 2, plus 1. So we know 2 times 2 is 4, plus 1 is 5. It worked. Let's try it all the way down here. I'm skipping a few. Y equals 2 times, now we're going to put in 5 for the input, and plus 1. So 2 times 5 is 10, plus 1. It works. So this rule, y equals 2x plus 1, perfectly describes this table, right? So this would be the new symbolic rule that represents the data that's inside this numerical table, right? Or an input-output table. Right? So from this input-output table, we were able to develop a rule. So this will be the first of my videos for lesson 1.1. Thank you for watching.